I'm very glad you're here. Before we settle in, tell me where in the world you're listening from. Maybe you're tucked into bed, stretched out on the sofa, or travelling somewhere late at night. Wherever you are, I hope you're warm and comfortable. If you enjoy these slow, sleepy explorations, a like and a subscribe helps more people find their way here. And if you've already subscribed, thank you. It means a great deal. 2 gentle notes before we drift off. We have an ebook available on the Sleepy Scientist website. There's a link in the description, and I'll leave a QR code on screen for the first 5 minutes. And we're now uploading episodes to Spotify, so if you'd rather close your eyes and listen without the glow of a screen, you can find us there too. Tonight, we're heading towards one of the most extraordinary events the universe can produce, the collision of 2 black holes, from a very safe distance, of course. We'll follow them as they spiral closer together, distort space-time around them, and finally merge into one, releasing gravitational waves that travel billions of light-years before reaching Earth. And perhaps most remarkably, we'll see how scientists learn to detect those waves at all, measuring changes in distance smaller than a proton, then using that tiny signal to reconstruct the final moments of objects we can never directly see. So, get comfortable and let's begin. What really happens when 2 black holes collide, and how can a faint ripple in space-time tell us the entire story? Black holes are famous for being invisible. Once matter or light crosses an event horizon, it cannot return to the outside universe, which means the black hole itself does not shine in the ordinary sense. And yet, when 2 black holes finally come together, the result can be one of the most energetic events anywhere in the cosmos. That sounds like a contradiction at first. 2 objects that cannot be seen directly can collide with extraordinary violence, release vast amounts of energy, and still produce almost no light at all. The reason is that the main signal does not come from glowing matter. It comes from space-time itself. When 2 black holes orbit one another, their gravity does not remain perfectly static. The geometry of space-time around them is changing continuously as the black holes move. If the orbit tightens and the motion becomes faster, those changes become more dramatic. Eventually, the system produces travelling distortions in space-time known as gravitational waves. These are not waves moving through some material medium. They're not like ripples on water, sound travelling through air, or vibrations passing along a rope. Gravitational waves are changes in the geometry of space-time itself, spreading outward from an accelerating distribution of mass. That distinction matters, because a black hole merger is not something astronomers normally watch in the way they might watch a star explode. If 2 black holes merge in an otherwise empty region of space, there may be very little ordinary light produced at all. There is no glowing surface on either black hole, and there does not need to be a bright cloud of gas surrounding them. Instead, the event can announce itself through gravity. The story begins long before the final collision. Imagine 2 black holes bound together in orbit, separated by a distance large enough that their motion is relatively slow. They circle their common centre of mass, each one moving through the curved space-time created by the entire system. As they orbit, they emit gravitational waves. Those waves carry energy away. Very gradually the orbit shrinks. The black holes move closer together, and as they do, they orbit faster. The gravitational waves become stronger. Their frequency increases. Their amplitude rises. This stage is known as the inspiral. For much of the inspiral, the system can evolve slowly, but near the end, the pace changes dramatically. The black holes begin circling one another several times in an extremely short period. Their orbital speeds reach a significant fraction of the speed of light, and the curvature of space-time around them becomes extraordinarily intense. Then comes the plunge. The orbit can no longer continue in anything resembling its earlier stable form. The black holes move together rapidly, and a single common event horizon forms around the system. This is what physicists mean when they describe 2 black holes as merging. The word collision can make the event sound more familiar than it really is. It is tempting to imagine 2 dark spheres flying into one another, rather like 2 solid balls striking each other in space. But black holes do not have solid surfaces. There is no crust to crack, no material shell to shatter, and no moment when 2 hard objects physically bounce together. Instead, the geometry surrounding the 2 black holes evolves until one connected black hole remains. That new black hole is not immediately calm. For a short time, it is distorted by the extraordinary event that created it. It vibrates gravitationally, losing the remaining distortions as another burst of gravitational waves. This final stage is known as Ringdown. The name is rather appropriate. The new black hole behaves, in a very loose sense, like a bell that has just been struck. It oscillates for a short time and then settles. Of course, there is no metal bell and no sound travelling through space. The thing that is ringing is space-time. For a very long time, all of this remained beyond direct observation. Then, on September 14th, 2015, something remarkable crossed Earth. A gravitational wave passed through the planet after travelling for roughly 1.3 billion years. It had been produced by two distant black holes during the final moments of their merger. By the time the wave reached Earth, its effect was almost absurdly small. It stretched and compressed the distances inside highly sensitive detectors by an amount far smaller than the width of a proton, and yet the pattern was there. The signal rose rapidly in both frequency and strength, producing what researchers call a chirp. This chirp lasted only a fraction of a second, but contained an astonishing amount of information. The way the frequency increased revealed how quickly the black holes were spiraling together. The strength of the signal helped describe the scale and distance of the event. The detailed shape of the waveform carried information about the masses of the black holes, their motion, and the properties of the black hole created after the merger. In other words, scientists did not need to see the black holes. They could read their motion from the shape of space-time itself. This changed astronomy in a fundamental way. Before gravitational wave observations, astronomers had already found many black holes indirectly by watching stars or hot gas moving around invisible massive objects. But binary black holes that contained little surrounding matter could remain almost completely hidden. Gravitational waves reveal that hidden population. They also opened a new way to test Albert Einstein's general theory of relativity. General relativity describes gravity as the curvature of space-time, and black hole mergers push that description into one of its most extreme possible environments. Gravity is strong. The objects are moving rapidly. Space-time is changing violently from moment to moment. There are very few places in nature where physicists can study gravity under conditions quite like these, and there is a beautiful contrast hidden inside the whole process. At the source, two black holes can release an extraordinary amount of energy through gravitational radiation in less than a second. Space and time around them are being distorted on a colossal scale. Yet after travelling across more than 1 billion light-years, the wave reaches Earth as something almost unimaginably gentle. It does not shake buildings. It does not noticeably move the ground. It passes through the planet, through oceans, through people, and through almost everything else without being felt at all. Only instruments built with astonishing precision can detect it. A vast cosmic collision becomes a movement smaller than an atomic nucleus. And inside that tiny movement is the story of two black holes, beginning with their final orbits, continuing through their merger, and ending with one new black hole quietly settling into the darkness. To understand what happens when two black holes merge, it helps to begin with something surprisingly difficult to answer in ordinary language. What exactly is a black hole? It is tempting to picture one as an extremely dense object sitting somewhere in space, perhaps like a dark sphere with a surface hidden from view. But that picture is only partly useful. In general relativity, a black hole is better understood as a region of space-time from which nothing can return to the outside universe once it has crossed a particular boundary. That boundary is the event horizon. The event horizon is not a wall, shell, membrane, or physical surface. A falling object would not strike it or feel itself passing through some solid barrier. Instead, the event horizon is a causal boundary created by the geometry of space-time. Beyond it, all possible future paths lead farther inward. Even light travelling at the greatest speed permitted by relativity cannot choose a route that carries it back outside. This is why the word black is so appropriate. Light from inside the horizon cannot escape to reach a distant observer. The mathematical foundations of this idea appeared remarkably soon after Albert Einstein presented his general theory of relativity. In 1916, the physicist Carl Schwarzschild found an exact solution to Einstein's field equations. The Schwarzschild solution describes the space-time surrounding an idealized object that has mass but does not rotate and carries no electrical charge. It eventually became clear that this solution contains the basic structure of what we now call a black hole. For a black hole described by the Schwarzschild solution, the size of the event horizon depends entirely on its mass. One useful scale is called the gravitational radius. It grows directly with mass, and for a non-rotating black hole, the event horizon lies at twice this gravitational radius. A black hole with roughly 10 times the mass of the Sun would have an event horizon only around 60 kilometers across. Increase the mass to several tens of suns, like many of the black holes discovered through gravitational waves, and the horizon still spans only a few hundred kilometers. That is an extraordinary concentration of mass. An object containing more material than dozens of suns can occupy a region comparable in scale to the distance between nearby cities. Real astrophysical black holes, however, are unlikely to be perfectly motionless. Stars rotate. Binary systems orbit. Collapsing matter carries angular momentum. When black holes merge, the enormous orbital angular momentum of the system also has to go somewhere. So a more realistic description was needed. In 1963, the mathematician Roy Kerr discovered another exact solution to Einstein's equations. The Kerr solution describes a rotating electrically neutral black hole. This is the form expected to describe most isolated astrophysical black holes and, importantly, the black hole left behind after two black holes merge. A rotating black hole differs in significant ways from the simpler Schwarzschild case. Rotation drags the surrounding space-time with it through an effect known as frame dragging. The shape and position of the horizon also depend on the black hole's spin, but even for a rotating black hole, the main properties visible from the outside remain remarkably simple. Mass tells us how much energy the black hole contains. Angular momentum describes its rotation. Electrical charge can also appear in the mathematical description, but real black holes in space are expected to retain very little net charge. Any substantial charge would attract surrounding particles carrying the opposite charge, tending to neutralize the black hole relatively quickly. For most astrophysical situations, mass and angular momentum are therefore the properties that matter most. Another concept often associated with black holes is the singularity. Classical general relativity predicts that matter inside a black hole ultimately encounters a region where the theory produces extreme behavior, commonly described as a singularity. In the simplest mathematical solutions, quantities such as space-time curvature can become unbounded there. But the singularity should not be confused with the event horizon. The horizon is the boundary separating regions that can still communicate with the distant universe from regions that cannot. The singularity lies deeper within the classical description. When astronomers detect gravitational waves from colliding black holes, they are not receiving signals from the singularities themselves. No information can travel outward through an event horizon once it has crossed inside. Instead, the observed gravitational waves are generated by the rapidly changing geometry outside and around the horizons as the entire system moves. That distinction is important. Much of the measurable physics of a merger can be studied without knowing the ultimate quantum description of whatever occurs at the deepest interior of a black hole. Many of the black holes detected in gravitational wave events belong to the stellar mass category. These can form when sufficiently massive stars reach the end of their lives and their cores collapse under gravity. The details depend on the star's original mass, chemical composition, mass loss, rotation, binary interactions, and the behavior of the collapse itself. Not every massive star becomes a black hole. Some leave neutron stars behind. Others lose so much material before collapse that the remaining core is relatively small. Very massive stars can also encounter different forms of instability that complicate the picture further. And once a black hole is formed, it may remain almost completely dark. Astronomers can sometimes detect one because a nearby star orbits an invisible massive companion. In other cases, gas falling towards a black hole becomes extremely hot and bright before crossing the horizon. Some accreting black holes also produce powerful jets of particles extending far into surrounding space. Gravity itself can reveal them as well. A black hole can bend light from background objects through gravitational lensing, and now gravitational waves provide another method entirely. Two black holes can orbit one another in darkness, with very little surrounding gas and almost no ordinary light to announce their existence. For most of their lives as a binary, they may also be far too widely separated for their gravitational waves to fall within the frequency range of detectors on Earth. Their orbit can shrink slowly for millions or even billions of years. For almost all of that time, nothing dramatic happens from our perspective. Then, during the final moments, the separation becomes small, the orbital frequency rises rapidly, and the gravitational waves enter the range that instruments on Earth can measure. A system that may have evolved quietly for longer than complex life has existed can reveal itself to us in only a fraction of a second. And beneath that brief signal are two remarkably simple objects. Not dark balls with surfaces, not holes punched through space, but regions where gravity has curved space-time so profoundly that the direction outward has disappeared from every possible future path. A single black hole can spend most of its existence travelling through space alone, but for two black holes to collide, something must first bring them together and keep them bound closely enough that gravity can slowly finish the job. There is no single confirmed pathway that explains every binary black hole system we observe. Instead, astronomers think nature may have several ways of arranging these mergers, each beginning under very different circumstances. One of the simplest possibilities starts not with black holes at all, but with two massive stars. Stars are often born in groups, and many massive stars are members of binary systems. In such a system, two stars orbit their common centre of mass, sometimes for millions of years, evolving side by side. If both stars are massive enough, each may eventually leave behind a black hole. That sounds straightforward, but keeping the pair together is surprisingly difficult. Massive stars change enormously during their lives. They lose material through powerful stellar winds. They swell into giant stars. They can transfer material to one another. Their cores collapse. Some explode as supernovae. Every one of these stages can alter the orbit. Suppose one star expands until its outer layers begin spilling onto its companion. This is known as mass transfer. Depending on how rapidly the material moves and how much is lost from the system, the orbit may shrink or widen. The two stars can exchange enormous amounts of matter before either has become a black hole. In more dramatic cases, one expanding star can engulf its companion inside a shared cloud of gas. This stage is called common envelope evolution. The companion then moves through the envelope, transferring orbital energy into the surrounding gas. If enough energy is deposited, much of the envelope can be expelled into space. At the same time, the orbit may contract dramatically. The result can be two stellar cores left much closer together than they were before. Common envelope evolution is potentially very important because a pair of black holes born extremely far apart might never merge within the age of the universe. Bringing the progenitor stars closer together gives the eventual black holes a much better chance. But this process remains difficult to model in detail. Gas flows in 3 dimensions, stars deform, material is expelled, and enormous differences in scale have to be followed simultaneously. The uncertainties are large enough that common envelope evolution remains one of the major challenges in understanding compact binary formation. Then there is stellar collapse itself. When the core of a sufficiently massive star can no longer support itself, gravity drives it inward. Depending on the star's mass and structure, the collapse can produce a neutron star or a black hole. Some collapsing stars may undergo powerful supernova explosions. Others may collapse more quietly. The newly formed compact object can also receive a sudden velocity known as a natal kick. If that kick is large enough, the binary may be disrupted completely. The two objects simply go their separate ways. If the system survives, its orbit may become wider, tighter, tilted, or more eccentric. This has to happen twice if both stars are to become black holes. So an isolated binary black hole is, in a sense, the survivor of an unusually complicated relationship. It has made it through mass loss, stellar expansion, possible mass transfer, perhaps a common envelope, core collapse, and potentially 2 natal kicks without being separated. Even then, this is only one possible origin. Black holes can also meet in crowded environments where gravitational encounters happen frequently. Globular clusters are particularly interesting places for this. These are dense, roughly spherical collections containing hundreds of thousands or even millions of stars. Over long periods, repeated gravitational encounters redistribute energy throughout the cluster. More massive objects tend gradually to sink towards the centre through a process connected with dynamical friction and mass segregation. Black holes are among the heaviest ordinary stellar remnants in such a cluster, so they can become concentrated in central regions. There, encounters between single black holes and existing binary systems become more common. A black hole passing close to a binary may interact strongly enough to replace one of its members. This is known as an exchange interaction. Because heavier objects are particularly effective at remaining in tightly bound systems, black holes can gradually assemble into binaries even if they were not born together. Further encounters can harden the binary, meaning that the two black holes become more tightly bound. Each interaction can remove some orbital energy while sending another object away at higher speed. Eventually, the binary can become compact enough that gravitational wave emission takes over and drives the final inward spiral. Similar processes may occur in nuclear star clusters surrounding the centers of galaxies, where stellar densities can become extreme. Another proposed environment is the gaseous disk around an active galactic nucleus. An active galactic nucleus contains a feeding supermassive black hole surrounded by gas. Smaller black holes moving through this disk may interact with the gas, alter their orbits, migrate through the disk, and encounter one another. Researchers are still working out how important this pathway might be, but it offers another possible place where black hole binaries can form efficiently. Dense environments also introduce a particularly intriguing possibility. A black hole may merge more than once. After two black holes collide, the remnant can remain inside a massive star cluster or another deep gravitational environment if the recoil from the merger does not eject it. That remnant can later encounter another black hole and form a new binary. If they merge, the final black hole now contains material that has already passed through an earlier merger. This is called hierarchical merging. Repeated mergers can produce black holes that are unusually massive compared with those expected from ordinary stellar collapse. They can also create distinctive spin properties because merger remnants are often left rotating rapidly. Some of the unusually massive black holes discovered through gravitational wave observations have therefore encouraged researchers to investigate whether hierarchical formation may be involved. There is also a much more speculative idea. Primordial black holes are hypothetical black holes that may have formed from unusually dense regions in the very early universe, rather than from collapsing stars. If they exist in suitable numbers and mass ranges, some could potentially form binaries and merge. At present, however, primordial black holes are not required to explain the observed gravitational wave population, and there is no accepted evidence showing that the detected mergers must involve primordial objects. They remain a possible idea rather than an established origin. Fortunately, the mergers themselves contain clues about where their black holes came from. One clue is mass. Different formation environments may favour different ranges of black hole masses, and different ratios between the heavier and lighter member of a binary. Another clue comes from spin. If two massive stars evolve together for a long time, their spins may sometimes retain a relationship with the plane of the orbit. In contrast, black holes assembled through random encounters in a dense cluster may have spin directions that are much less orderly. A strongly tilted or apparently random spin configuration can therefore hint at dynamical formation, although no single measurement provides an unambiguous answer. The overall distribution matters more than any one system. By collecting many mergers, astronomers can study patterns in mass, spin, orbital shape, and merger rate, and compare them with models of stellar evolution and dense stellar environments. The picture is still developing. There may not be one dominant route. Some black holes may begin as stellar partners, others may meet much later inside clusters. A few may have merged before, yet every pathway eventually reaches the same physical requirement. The orbit must lose energy. As long as two black holes remain widely separated, they can circle one another for extraordinary lengths of time. But once enough orbital energy begins to leave the system, their separation starts to decrease. Their motion becomes faster, their gravitational influence changes more rapidly, and gradually, almost imperceptibly at first, the two black holes begin the long inward journey that will eventually bring their horizons together. For two black holes to spiral together, something must be carrying energy away from their orbit. That something is not light, gas, or any other ordinary material. It is a disturbance in the structure of space-time itself. The idea comes from Albert Einstein's general theory of relativity, published in 1915. Before Einstein, gravity was usually understood through Isaac Newton's description, in which massive objects attract one another with a force. Newton's theory works extraordinarily well for many everyday situations, from falling objects to planetary orbits. Einstein changed the picture. In general relativity, gravity is not treated as an ordinary force reaching across space. Instead, mass and energy affect the geometry of space-time, and objects move through that curved geometry. The Sun, for example, changes the structure of space-time around it. Earth follows a path through that curved space-time, producing what we experience as an orbit. The same principle applies to black holes, only much more intensely. A black hole curves space-time strongly because its mass is concentrated within a very small region. Place two black holes in orbit around one another, and the geometry becomes dynamic. The mass distribution is constantly changing as the black holes move. Those changes do not remain confined to the immediate neighbourhood of the binary, they can propagate outward. In 1916, Albert Einstein showed that his equations allowed wave-like disturbances in gravity. He refined the calculation further in 1918. These disturbances became known as gravitational waves. Their existence was not immediately accepted as an obvious physical fact. For decades, physicists debated whether gravitational waves represented genuine travelling phenomena or merely mathematical features produced by particular choices of coordinates. Part of the difficulty came from the strange nature of general relativity itself. Space-time is not simply a fixed background where gravity happens. Space-time is part of the physics. Eventually, the interpretation became much clearer. Gravitational waves are real changes in the geometry of space-time that carry energy away from their source. One useful way to imagine them is to picture a ring of freely floating particles in empty space. As a gravitational wave passes through the ring, the particles are not pushed around in the ordinary sense. Instead, the distances between them change. For one part of the wave, the ring may stretch vertically while being compressed horizontally. A moment later, the pattern reverses. It stretches horizontally and compresses vertically. This is why gravitational waves are described as transverse. Their distortions occur across directions perpendicular to the direction in which the wave is travelling. General relativity predicts two standard patterns of this distortion. They are known as plus polarization and cross polarization. With plus polarization, the stretching and squeezing occur along two perpendicular directions that might be imagined as vertical and horizontal. Cross polarization produces the same basic alternating effect, but rotated by roughly 45 degrees. A real detector responds differently depending on the direction from which the gravitational wave arrives, and how these polarizations are oriented relative to the detector. By the middle of the 20th century, physicists had become increasingly interested in whether these waves could transfer genuine energy. Hermann Bondi and Felix Pirani were among the researchers who helped clarify the physical interpretation of gravitational radiation. Richard Feynman also contributed a particularly memorable thought experiment during a conference in the 1950s. It became known as the sticky bead argument. Imagine a rod with beads threaded onto it. The beads can slide along the rod, but friction resists their motion. If a gravitational wave passes through, it changes the distance between the beads. The beads move relative to the rod. Friction generates heat, and energy has therefore been transferred into the system. If a gravitational wave can cause heating, then it cannot simply be a meaningless mathematical artifact. It must carry real energy. That energy travels outward from the source at the speed of light. As the wave expands across larger and larger regions of space, its influence becomes weaker. By the time a gravitational wave produced by a distant black hole merger reaches Earth, the distortion can be extraordinarily small. Physicists describe the size of this distortion using a quantity called strain. Strain compares the change in a length with the original length being measured. In spoken form, the relationship is simply strain equals the change in length divided by the original length. Strain has no physical unit because it compares one length with another. A strain of around 1 part in 10 to the power of 21 means that a distance changes by only 1 part in a billion trillion. This is roughly the scale that modern gravitational wave observatories are designed to detect. Not every moving mass creates strong gravitational waves. A perfectly spherical object that expands and contracts symmetrically does not normally radiate gravitational waves in the same way. That is because gravitational radiation depends on an asymmetric changing distribution of mass. More precisely, the leading form of gravitational radiation comes from changes in what physicists call the mass quadrupole moment. An orbiting binary naturally provides exactly this kind of changing arrangement. The two objects are continually moving around their common centre of mass. Their mass distribution changes direction over and over again. For ordinary stars or planets, the gravitational waves produced are generally far too weak to detect across astronomical distances. Black holes are different. They can contain enormous masses while orbiting extremely close together at extraordinary speeds. That combination produces much stronger changes in space-time. As two black holes circle each other, gravitational waves continuously carry energy and angular momentum away. The binary, therefore, has slightly less orbital energy after each orbit than it had before. The separation shrinks, the orbital speed rises, the gravitational waves become stronger and arrive more frequently. So the path towards collision is built directly into Einstein's theory. The black holes do not simply happen to drift together. Their orbit is continuously reshaping space-time, and the ripples produced by that changing geometry are slowly carrying away the very energy that keeps them apart. Every gravitational wave leaving a binary black hole system carries something with it: energy and angular momentum. That loss is tiny when the two black holes are far apart, but it has an unavoidable consequence. The orbit cannot remain exactly the same forever. As energy leaves the system, the black holes gradually move closer together. Their orbit becomes tighter. They circle one another more quickly, and the closer they become, the more efficiently they produce gravitational waves, which remove still more energy from the orbit. This creates a slow but steadily accelerating inward spiral known as the inspiral. For widely separated black holes, the early part of this process can be extraordinarily gentle. The two objects may complete orbit after orbit, while their separation changes by only a minute amount. Given enough time, however, those tiny losses accumulate. An important clue that this process was real appeared decades before gravitational waves were detected directly. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a remarkable binary system containing a pulsar. A pulsar is a rapidly rotating neutron star that emits highly regular beams of radiation. As the star spins, those beams can sweep across Earth with extraordinary precision, producing pulses that behave almost like the ticks of a cosmic clock. The system discovered by Russell Hulse and Joseph Taylor contained two neutron stars orbiting one another. It was not a pair of black holes, but the same fundamental gravitational principle applied. According to Albert Einstein's general theory of relativity, the orbiting neutron stars should emit gravitational waves. Those waves should carry energy away, causing the orbit to shrink. And that is exactly what observations revealed. By timing the pulses over many years, astronomers measured the orbital period becoming slightly shorter. The rate of change closely matched the prediction of general relativity. It was powerful indirect evidence that gravitational waves were not merely mathematical possibilities. Real astronomical systems were apparently losing orbital energy in exactly the way Einstein's theory predicted. Russell Hulse and Joseph Taylor later received the Nobel Prize in Physics in 1993 for the discovery and its implications. Black hole binaries behave according to the same broad principle. When the black holes are very far apart, their gravitational wave emission can be weak, and the inward migration may take millions or billions of years. But the process does not continue at a constant pace. As the orbital separation decreases, the black holes move more rapidly. Faster motion produces stronger gravitational radiation. Stronger radiation carries away energy more efficiently. The orbit then shrinks even more quickly, so the inspiral accelerates naturally. For most of the binary's lifetime, almost nothing seems to happen. Then the final stages arrive with astonishing speed. The gravitational wave frequency also changes as the orbit evolves. For two black holes moving on a nearly circular orbit, the strongest gravitational wave pattern usually has a frequency approximately twice the orbital frequency. In simple terms, if the black holes complete one orbit, the dominant gravitational wave pattern goes through roughly 2 cycles. As the black holes move closer together and orbit more rapidly, the gravitational wave frequency rises. At the same time, the signal becomes stronger. If the wave is converted into an audible form, this combination creates the famous chirp associated with a compact binary merger. The sound begins at a lower pitch and rapidly sweeps upward. The rising pitch represents increasing frequency. The growing strength reflects the increasing amplitude of the gravitational wave. Both changes are consequences of the same inward spiral. One of the quantities that strongly controls how quickly this chirp evolves is known as the chirp mass. The chirp mass is not simply the total mass of the two black holes. It is a particular combination of their individual masses, This combination determines much of the rate at which the orbital frequency increases during the inspiral. By measuring how quickly the gravitational wave sweeps upward in frequency, physicists can therefore estimate the chirp mass with remarkable precision. The overall masses of the system also determine how long the signal remains within the sensitive frequency range of a detector on Earth. Lighter binary systems generally orbit more rapidly before merging at higher gravitational wave frequencies. They can spend many more cycles moving through the frequency band where ground-based detectors are sensitive. More massive black holes merge at lower characteristic frequencies. Their final inspiral may therefore pass through the detector's sensitive range much more quickly. A very massive binary can announce itself with only a relatively small number of observable cycles before the merger arrives. The shape of the orbit matters as well. Binary orbits can be eccentric, meaning they are stretched into ellipses rather than being nearly circular. Gravitational wave emission tends to reduce that eccentricity over time. Energy is radiated particularly strongly during the closest parts of an eccentric orbit, gradually pushing the system towards a more circular configuration. For binaries that have spent a long time spiraling inward in isolation, astronomers therefore expect the orbit to be almost circular by the time the gravitational waves become detectable from Earth. But this also creates an opportunity. If a merger entered the detector band with clearly measurable eccentricity, it could provide evidence that the binary formed relatively recently through gravitational encounters in a crowded environment such as a dense star cluster. The waveform can therefore preserve clues not only about the final moments of the black holes, but about how they met in the first place. Throughout most of the inspiral, physicists can describe the orbit using mathematical approximations that build progressively upon the familiar ideas of Newtonian gravity, while including corrections from general relativity. These methods work extremely well when the black holes are still sufficiently separated and their motion is not yet dominated by the most extreme nonlinear effects of gravity. But eventually the separation becomes too small. The orbital speed becomes too great. The curvature of space-time becomes too strong. The slow, orderly picture of two objects gently losing energy, orbit by orbit, begins to break down. What may have taken billions of years to approach is suddenly compressed into moments. The long inspiral is almost over, and the two black holes are entering a region where gravity can no longer be treated as a small correction to the familiar motions of ordinary celestial objects. By the time two black holes reach their final orbits, the slow and patient character of the inspiral has changed completely. The black holes are now close enough that space-time around them is strongly curved. Their orbital speed has risen to a substantial fraction of the speed of light, and the familiar picture of two objects moving along neat, almost Newtonian paths begins to lose its usefulness. Gravity is no longer a small correction to an otherwise simple orbit. It dominates everything. Physicists often describe the transition from inspiral to plunge as though there were a single decisive boundary between the two. That language is useful, but for two black holes of comparable mass, reality is more complicated. There is not always one precise moment when a stable orbit suddenly ends and a plunge begins. Instead, the motion gradually becomes more rapid, more strongly relativistic, and more difficult to separate into distinct stages. One idea that helps explain this transition is the innermost stable circular orbit. For a small object orbiting a much larger black hole, general relativity predicts a minimum distance at which a stable circular orbit can exist. Outside this region, a small object can remain in orbit if it has the correct speed. Move inward far enough, however, and stable circular motion is no longer possible in the same way. The object begins to fall inward rapidly. This idea is particularly clean when one object is tiny compared with the black hole it orbits. A real binary black hole merger is usually more complicated because both objects can have substantial masses, both distort space-time strongly, and neither is simply moving through the fixed gravitational field of the other. Still, the innermost stable circular orbit remains an important conceptual guide to the conditions near the end of an inspiral. The details of those final orbits depend strongly on the black holes themselves. Their total mass matters. The ratio between their masses matters. Their spins matter. Even the directions in which those spins point can alter the waveform that eventually reaches Earth. If the black holes have similar masses, the system may appear relatively balanced. If one is much heavier, the motion becomes more asymmetric. rotation adds another layer. A rotating black hole does not simply sit inside space-time. According to general relativity, it drags the surrounding geometry around with it. This effect is known as frame dragging. Near a rapidly rotating black hole, space-time itself is effectively twisted in the direction of the rotation. When the spins of two merging black holes are aligned neatly with their orbit, the motion can remain relatively orderly. But if those spins point in different directions, the orbital plane itself can begin to wobble. This motion is known as precession. Instead of the binary orbit remaining fixed in one plane, its orientation changes over time. That precession leaves patterns in the gravitational wave. The signal can become subtly modulated in amplitude and phase, allowing researchers to infer information about the spins and their directions. As the black holes continue inward, the orbital speeds become extreme. There is no single velocity that applies to every merger, because the value depends on mass, spin, separation, and exactly how the orbital speed is defined in such strongly curved spacetime. But near merger, the black holes are moving at a significant fraction of the speed of light. The timescales shrink dramatically as well. For stellar mass black holes, the orbital period during the final stages can be measured in milliseconds. A journey that may have taken millions or billions of years to develop can end with several crucial revolutions packed into a tiny fraction of a second. Much of the earlier Inspiral can be described using methods known as post-Newtonian approximations. These calculations begin with the familiar structure of Newtonian gravity and then add increasingly sophisticated corrections from general relativity. When the black holes are still reasonably far apart and moving at speeds that are not too extreme, these approximations can describe the system with impressive accuracy. Closer to merger, however, the gravitational field becomes strongly nonlinear. The geometry created by the two black holes is changing rapidly, and the gravitational field itself participates in the dynamics. The old approximations become progressively less reliable. Physicists therefore developed other techniques to bridge the gap between the orderly inspiral and the violet merger. One important example is the effective one-body approach developed by Alessandra Buonanno and Thibaut Damour. The method transforms the complicated motion of two interacting bodies into an equivalent problem that can be treated, in a useful mathematical sense, as one effective body moving through a specially constructed relativistic spacetime. Combined with other calculations and numerical simulations, this approach has become extremely valuable for predicting complete gravitational waveforms, and all the while, the physical event remains strangely quiet in the ordinary sense. The black holes do not crash together with a flash simply because their horizons approach. There are no solid surfaces to strike. There is no material shell to break apart. If the surrounding region contains little gas, there may be almost no electromagnetic display at all. There is also no sound in empty space. Any sound would require matter such as gas to carry pressure waves, and a clean binary black hole merger may provide very little of it. The violence appears instead through gravity. As the black holes move faster and the mass distribution changes more rapidly, the gravitational waves increase in strength. Their amplitude reaches its greatest value around the merger itself. At this point, the orbit is no longer gently evolving from one nearly stable configuration to another. The entire gravitational system is changing on almost the same timescale as the motion of the black holes. Space-time is being distorted, twisted, and rearranged with extraordinary speed. The two separate regions associated with the original black holes are approaching a profound change. Soon, describing the system as two independent black holes will no longer make sense. A single connected horizon will enclose them. And for a brief moment, the most useful way to understand the event is not as two objects crashing together, but as space-time reorganizing itself into one new black hole. When physicists say that two black holes merge, they do not mean that two solid objects smash together and break apart. What actually happens is stranger, and in many ways more elegant. As the black holes approach one another, the regions of space-time surrounding them become increasingly distorted. Each black hole has its own event horizon, the boundary beyond which no future path can lead back to the distant universe. During the final plunge, those two separate horizons give way to a single common event horizon enclosing the system. At that point, it is no longer meaningful to describe the outside universe as containing two distinct black holes. There is now one. The event horizon itself is a subtle object. It is not a glowing surface that an observer could watch stretching, touching, and joining in the ordinary sense. An event horizon is defined by the global structure of space-time. It separates paths that can eventually escape to great distances from paths that can never return. That means identifying the exact event horizon requires knowledge of how space-time develops into the future. In other words, the boundary is partly defined by what ultimately happens to light and matter that try to escape. This is one reason simulations often use another closely related idea known as an apparent horizon. An apparent horizon can be identified using information about space-time at a particular moment, or more precisely on a particular mathematical slice through the simulated space-time. It marks a surface from which outward-directed light rays are no longer expanding away in the usual manner. Because apparent horizons can be located using information available within the simulation at that time, they're extremely useful for tracking black holes as they orbit and merge. The event horizon and apparent horizon are related, but they are not exactly the same thing. During a calm, settled black hole, the distinction can become relatively straightforward. During a violent merger, however, the geometry is changing so rapidly that the difference matters. As the two black holes coalesce, the newly formed common horizon is not immediately a smooth and perfectly calm sphere. It is distorted. It can be stretched and elongated by the motion that created it. The space-time around it is still carrying the imprint of two massive objects that were orbiting at enormous speed only moments earlier. The new horizon therefore changes shape dynamically as the remnant begins to settle. From far away, an observer can receive gravitational waves produced by this changing exterior geometry. That does not mean information is escaping from inside the completed horizon. Nothing that has crossed the event horizon can send a signal back out. The gravitational waves detected at great distances come from the behavior of space-time outside the horizon as the system evolves. This point helps clear up one of the most common misleading pictures of a black hole merger. Black holes are often drawn with a central point representing a singularity, which can make it seem as though two tiny dense objects must eventually strike one another somewhere in the middle. But the singularity is not a little ball sitting inside the horizon. In classical general relativity, a singularity represents a breakdown in the usual description of space-time, where quantities such as curvature can become extreme and the mathematical theory reaches its limits. The internal structure of a realistic rotating merger is much more complicated than two dots simply colliding. After the merger, general relativity predicts one connected black hole interior, but the precise structure deep inside cannot be observed directly from the outside universe. And because a complete theory of quantum gravity does not yet exist, physicists do not claim to understand every aspect of the deepest interior. There is also an important idea associated with the mathematician and physicist Roger Penrose known as cosmic censorship. In broad terms, cosmic censorship suggests that singularities produced in realistic gravitational collapse are hidden behind event horizons rather than appearing exposed to the wider universe. A naked singularity, if one could form, would present serious conceptual problems because regions where classical general relativity breaks down could potentially influence distant observers directly. Cosmic censorship remains a conjecture rather than a proven law of nature. Black hole mergers nevertheless appear to behave in a way consistent with the idea that the extreme interior remains concealed behind a horizon. Outside that horizon, the merger follows Albert Einstein's equations with remarkable precision. The newly formed black hole also does not simply inherit the exact combined mass of the original pair. Some of the system's energy has already escaped. The gravitational waves emitted during the inspiral, plunge, merger, and settling process carry real energy away from the binary. Because mass and energy are connected, the final black hole therefore usually has slightly less mass than the combined masses of the two original black holes. The difference can be substantial. In powerful stellar mass black hole mergers, several times the mass of the Sun can effectively be carried away in the form of gravitational radiation. The remnant will also almost always rotate. Before merger, the binary contains a large amount of orbital angular momentum, simply because the black holes are circling one another. The individual black holes may also be spinning. Angular momentum cannot simply disappear. Some is carried away by gravitational waves, while the rest remains in the final black hole. Unless the orbital angular momentum and individual spins happen to cancel with extraordinary precision, the remnant is therefore a rotating black hole. There is no cosmic tear at the moment the horizons become one. Space-time does not split open. Nothing breaks through some hidden boundary of the universe. What occurs is extreme, but it is still lawful. The geometry that once described two separate black holes evolves into the geometry of one distorted, rotating black hole. For a brief time, that remnant continues to change violently. Then the excess distortions begin to fade away as gravitational waves continue carrying energy outward. The collision is over. Two horizons have become one, and the final black hole begins the quieter process of settling into its new form. The final moments of a black hole merger are so extreme that ordinary calculation begins to struggle. Albert Einstein's field equations describe how matter and energy shape spacetime, and how that curved spacetime in turn influences the motion of matter and energy. In gentle situations, physicists can often simplify those equations or use carefully constructed approximations. But when two black holes are only moments from merging, almost nothing about the situation is gentle. The gravitational fields are enormously strong. The black holes are moving at a substantial fraction of the speed of light. The geometry of space-time is changing almost as quickly as the black holes themselves are moving, and most importantly, gravity becomes strongly nonlinear. Nonlinear gravity means that the behavior of the gravitational field cannot be treated as a simple sum of separate influences. In weaker situations, it can sometimes be useful to imagine the gravity from one object being added to the gravity from another. Near a black hole merger, that picture becomes inadequate. The gravitational field itself carries energy. That energy contributes to the evolving geometry. The geometry then influences the motion of the black holes, which changes the gravitational field again. Everything is coupled together. This is why the merger cannot simply be calculated by following two neat objects along predetermined paths. Physicists must solve the changing spacetime itself. The field devoted to doing this with computers is known as numerical relativity. Instead of trying to find one elegant equation that describes the entire merger from beginning to end, numerical relativity divides the problem into enormous numbers of smaller calculations. A computer represents a region of space-time mathematically. It then calculates how that geometry changes over a tiny interval. The result becomes the starting point for the next interval. Repeated again and again, this allows researchers to follow a black hole binary as it orbits, plunges together, forms a common horizon, and settles into a final remnant. That sounds straightforward in principle. In practice, it took decades to make it work reliably. Black holes contain regions where the classical equations produce singular behavior. If a computer simulation handles those regions badly, numerical values can grow uncontrollably and destroy the calculation. There is also the problem of coordinates. General relativity allows physicists considerable freedom in how they label locations and moments in space-time. A poor coordinate choice can make a perfectly reasonable physical situation appear numerically unstable. Computers must also handle very different scales at once. The region near each black hole requires extremely fine resolution. At the same time, the simulation must extend far enough outward to track gravitational waves propagating away from the source. The relevant timescales vary enormously as well. A long inspiral may evolve comparatively slowly, while the merger itself unfolds with breathtaking speed. For many years, complete stable simulations of comparable mass black hole mergers remained frustratingly difficult. Then, in 2005, the situation changed. Franz Pretorius achieved the first stable simulation that followed two orbiting black holes through merger and into the final remnant. Independent breakthroughs followed from other research teams, including work by Manuela Campanelli and Carlos Lusto, and by John Baker, Joan Centrella, Bernard Kelly, and James Van Meter. Together, these advances transformed the field. Two broad techniques became especially important. Franz Pretorius used an approach based on generalized harmonic coordinates. Other teams developed what became known as the moving puncture method. Both techniques, in different ways, allowed the simulations to handle the extreme geometry near black holes without the calculation collapsing into numerical chaos. The moving puncture approach treated the troublesome interior regions in a way that allowed their mathematical representations to move across the computational grid while the surrounding space-time remained stable. The generalized harmonic approach used a carefully controlled coordinate system to keep the equations well behaved as the black holes evolved. The important result was the same. For the first time, researchers could reliably watch the entire sequence unfold inside a computer. The simulations track far more than the black hole's apparent positions. They calculate the curvature of space-time, they locate horizons, they follow orbital motion, they determine the gravitational radiation escaping from the system. They estimate the final mass and spin of the remnant. They can even calculate whether uneven gravitational wave emission gives the new black hole a recoil, sending it away from the merger with a substantial velocity. By repeating these calculations for different systems, researchers have built enormous libraries of predicted gravitational waveforms. Some simulations contain nearly equal mass black holes, others use very unequal masses. The black holes may rotate rapidly or slowly. Their spins may point in the same direction as the orbit, against it, or at awkward angles that cause the system to precess. Each arrangement leaves a slightly different signature in the gravitational waves. These catalogues now contain thousands of numerical waveforms and related models, covering a broad range of possible mergers. They're essential because real gravitational wave detectors do not simply announce that a black hole merger has occurred. They produce a stream of data. To understand what caused a signal, researchers compare its structure with predictions from relativity. If the observed waveform follows the expected pattern of inspiral, merger, and ringdown for two black holes with particular masses and spins, confidence in the interpretation rises dramatically. Numerical relativity therefore creates a direct bridge between Albert Einstein's equations and the data measured on Earth. It predicts what a collision should look like in gravitational waves before the signal is ever observed. This is also worth remembering when looking at dramatic animations of merging black holes. Those images are not photographs. No telescope has taken a conventional picture of two event horizons visibly crashing together. The glowing surfaces, curved grids, coloured distortions and flowing shapes used in visualizations are representations of numerical calculations. They turn mathematics into something the eye can follow. The physics underneath them is real. And when an observed gravitational wave closely matches what those calculations predict, the simulation becomes more than a visual aid. It becomes evidence. The fading end of that predicted waveform belongs to a single, newly formed black hole. The complicated dance of two objects has ended. What remains is one distorted remnant, carrying the mass and angular momentum left behind after the gravitational waves have taken their share. For a brief moment, even that new black hole is not completely settled. Its space-time continues to oscillate, and those final vibrations carry one last message outward. Once the two black holes have merged, the most violent part of the collision is over, but the new black hole is not yet completely calm. The common horizon that forms during the merger is initially distorted by the enormous motion and gravitational forces that created it. It has inherited the combined mass, much of the angular momentum, and the complicated space-time geometry of the original binary. For a brief period, the remnant oscillates. This final stage is known as ringdown. The name comes from a familiar comparison. If a bell is struck, it vibrates at particular frequencies and gradually becomes quieter as those vibrations fade. A newly formed black hole behaves in a somewhat similar mathematical way. But there is no metal surface moving back and forth. There is no material shell. And there is certainly no ordinary sound travelling through empty space. What is oscillating is the geometry of space-time itself. The distorted black hole gradually relaxes towards the stable form, predicted by the Kerr solution, which describes a rotating black hole in general relativity. As it settles, the remaining distortions are carried away as gravitational waves. These vibrations are not random. They occur in characteristic patterns known as quasi-normal modes. Each quasi-normal mode has its own frequency and its own damping time. The frequency describes how rapidly the space-time oscillates. The damping time describes how quickly that oscillation fades. Unlike the perfectly sustained vibration of an idealized musical instrument, a black hole's modes lose energy rapidly. That is why they're called quasi-normal rather than normal modes. They are natural patterns of vibration, but they do not continue indefinitely. Important theoretical work on these oscillations was carried out by physicists including Kalin Vishveshwara, Saul Tucholsky, William Press, and Subramanian Chandrasekhar. Their studies helped establish how disturbances around black holes evolve, and how gravitational waves can carry those disturbances away. One particularly useful feature of Ringdown is its simplicity. The frequencies of the quasi-normal modes depend mainly on the mass and spin of the final black hole. A more massive black hole generally oscillates at a lower characteristic frequency. A lighter black hole rings more rapidly. Spin changes the pattern as well. A rapidly rotating remnant alters the frequencies and damping times of its modes, meaning that the ringdown signal contains information about how quickly the final black hole is turning. This gives physicists a remarkable opportunity. If the mass and spin inferred from the earlier inspiral and merger agree with the mass and spin inferred from the ringdown, then the entire signal is behaving consistently with Albert Einstein's general theory of relativity. The ringdown also connects with an important idea known as the no-hair theorem. The phrase is slightly playful, but the physics behind it is serious. In general relativity, an isolated black hole that has finished settling is expected to be extraordinarily simple. Its external gravitational field can be described by only a small number of properties. For an astrophysical black hole, the important ones are mass and angular momentum. Electrical charge is allowed mathematically, but real black holes in space are expected to carry very little lasting net charge. All the complicated details of how the black hole formed are therefore expected to disappear from its final exterior description. Whether the original objects came from massive stars, previous mergers, or some other route, a settled black hole should eventually be described by the same basic Kerr geometry if its mass and spin are the same. This expectation can be tested through something known as black hole spectroscopy. The name comes from the way astronomers study atoms and stars by examining characteristic frequencies in light. With black holes, the idea is to measure several quasi-normal modes in the gravitational wave ringdown. If those modes all correspond to the same mass and spin, they provide evidence that the remnant behaves like a Kerr black hole. If they did not fit together properly, that could indicate either an observational problem or something genuinely unexpected in the physics of strong gravity. In practice, measuring several ringdown modes is extremely difficult. The signal fades rapidly, and by the time the ringdown begins, the gravitational wave is already weakening. For stellar mass black hole mergers, the strongest ringdown can last only a fraction of a second. That means detectors have very little time to gather information. Still, particularly strong signals can reveal more detail, and increasingly sensitive observatories are making black hole spectroscopy more realistic. The final black hole may also leave the merger moving through space. This happens because gravitational waves are not always emitted equally in every direction. If the original black holes had different masses or complicated spin configurations, one side of the system can radiate slightly more momentum than the other. Momentum must remain balanced. So the remnant receives a recoil in the opposite direction. This is often called a gravitational kick. For some mergers, the kick may be relatively modest. In extreme theoretical configurations, it can reach thousands of kilometers per second. A sufficiently strong recoil could even eject a black hole from a dense star cluster, or, in exceptional cases, from a small galaxy. So the final remnant can emerge not only spinning, but travelling away from the place where the collision occurred. Meanwhile, the ringdown continues to fade. The distorted horizon becomes smoother. The strongest oscillations disappear. Space-time around the remnant approaches the stable Kerr geometry predicted by general relativity. After the enormous complexity of the inspiral and merger, the result is almost surprisingly simple. One black hole remains. It has a particular mass. It has a particular spin. And it may be moving through space because of the recoil. But one important question is still hidden inside that simplicity. The final black hole does not contain quite as much mass as the two original black holes did together. Some of the system has gone missing from the remnant. It has not vanished. It has escaped across the universe in the gravitational waves produced during the inspiral, merger, and ringdown. And because mass and energy are two forms of the same physical quantity, the difference tells us just how much energy this apparently dark collision was able to release. The black hole left behind after a merger is usually lighter than the two original black holes added together. At first, that might sound as though some of the mass has simply disappeared, but nothing has vanished. The missing mass has become energy. This connection between mass and energy is captured by one of Albert Einstein's most famous relationships. Energy equals mass multiplied by the speed of light multiplied by the speed of light. Because the speed of light is so enormous, Even a relatively small amount of mass corresponds to an extraordinary quantity of energy. A black hole merger demonstrates this on a scale almost impossible to reproduce anywhere else in nature. During the final inspiral, merger, and ringdown, gravitational waves carry energy away from the system. For particularly massive stellar black hole mergers, the amount released can be equivalent to several times the mass of the Sun. The first directly detected black hole merger provides a remarkable example. Gravitational wave event 150914 began with two black holes containing roughly 36 and 29 times the mass of the Sun. Together that gives approximately 65 solar masses. After the merger, however, the newly formed black hole contained only about 62 solar masses. Roughly 3 solar masses were missing from the remnant. Those 3 solar masses had not been destroyed. Their mass energy had been carried outward, predominantly in the form of gravitational waves, and most of that enormous release occurred over an extremely short period around the merger. To appreciate the scale, the Sun converts only a small amount of its mass into energy every second through nuclear fusion. Yet that process is enough to power almost all life on Earth. A black hole merger can effectively convert several entire suns worth of mass into gravitational radiation in less than a second. For a fleeting moment, the power emitted as gravitational waves can exceed the combined electromagnetic luminosity of all the stars in the observable universe. That comparison needs a little care. It refers to instantaneous power, meaning energy released per unit time. It does not mean that a black hole merger produces more total energy than every star throughout the history of the universe. Stars continue shining for millions, billions, or even trillions of years depending on their mass. The merger reaches an astonishingly high power because an immense amount of energy is released in an extremely brief interval, and despite all of that, a distant merger poses no danger to Earth. Gravitational waves spread outward as they travel across the universe. By the time they have crossed hundreds of millions or billions of light years, their effect has become extraordinarily weak. When the waves from gravitational wave event 150914 reached Earth, the measured strain was only around 1 part in 10 to the power of 21. The source was enormously violent. The effect here was almost unimaginably delicate. Energy is not the only quantity carried away. Gravitational waves also transport angular momentum. Before merger, much of the system's angular momentum is stored in the orbital motion of the two black holes, together with whatever spin each black hole already possesses. As gravitational waves leave the system, they remove some of that angular momentum. The remainder becomes part of the rotating remnant. This is why the final black hole is generally expected to spin. A typical merger contains so much orbital angular momentum that producing a completely non-rotating final black hole would require an extraordinarily precise cancellation between the orbital motion and the individual black hole spins. The remnant therefore usually becomes a Kerr black hole with substantial rotation. There is, however, a limit. According to general relativity, a Kerr black hole cannot simply be spun faster and faster without bound. There is a maximum allowed rotation relative to its mass. Astrophysical merger remnants are expected to remain below this extreme limit, partly because gravitational waves carry angular momentum away during the collision. The radiation can also leave the system unevenly. If the two black holes have different masses, or if their spins are arranged asymmetrically, the gravitational waves may be emitted more strongly in one direction than another. The escaping radiation then carries net momentum. Conservation of momentum requires the final black hole to move in the opposite direction. This is gravitational recoil, often called a gravitational kick. For some mergers, the kick may amount to tens or hundreds of kilometers per second. More extreme arrangements can produce much larger values. Numerical relativity predicts that carefully arranged combinations of unequal masses and rapidly rotating black holes can create recoil speeds of several thousand kilometers per second. That is fast enough to have genuine astronomical consequences. A black hole born inside a globular cluster might be kicked completely out of the cluster. In some cases, a sufficiently strong recoil could remove a black hole from a small galaxy. In deeper gravitational environments, the remnant may remain bound but end up travelling through its surroundings on a very different orbit. There is another remarkable constraint on the merger. In the early 1970s, Stephen Hawking showed that within classical general relativity, the total area of black hole event horizons should never decrease in any ordinary physical process. This is known as the black hole area theorem. If two black holes merge, the area of the final event horizon should therefore be at least as large as the combined areas of the original horizons. The result may sound surprising because the final black hole has lost some mass energy through gravitational waves, but horizon area depends on both mass and spin, and the full relativistic calculation preserves the required relationship. With sufficiently clear gravitational wave signals, physicists can compare estimates of the original black holes with the properties of the final remnant and test whether the area theorem holds. So the collision leaves behind far more than a single dark object. The final black hole carries the remaining mass. It retains much of the original angular momentum. It may be spinning rapidly. It may have received a recoil that sends it racing through its surroundings. And surrounding it, already travelling outward at the speed of light, is the energy that did not remain behind. Those gravitational waves can cross galaxies, pass through intergalactic space, and continue for billions of years. Eventually, a tiny fraction of that disturbance may reach Earth. The source may have released the mass energy of several suns, but here, the change in space-time is so small that detecting it requires some of the most precise instruments humanity has ever built. The gravitational waves produced by a black hole merger do not stop once the collision is over. They continue outward. They pass through the surrounding galaxy, cross intergalactic space, and may travel for hundreds of millions or billions of years before eventually reaching Earth. By then, the original event is long finished. The black holes have merged. The remnant has settled. The source may now be separated from us by an enormous distance, and yet the disturbance in space-time continues moving at the speed of light. When it finally reaches Earth, it passes through remarkably quickly. A signal that spent more than 1 billion years crossing the universe may sweep through a detector in less than a second. The challenge is noticing it. Gravitational waves interact so weakly with matter that almost everything on Earth simply lets them pass through. That is useful because the signal can travel enormous distances without being absorbed. But it also makes detection extraordinarily difficult. To measure these waves, physicists built instruments designed to notice tiny changes in distance. The most famous of these is the Laser Interferometer Gravitational Wave Observatory. It consists of 2 large observatories in the United States. One is near Hanford in Washington. The other is near Livingston in Louisiana. The idea grew through decades of theoretical and experimental work. Rainer Weiss played a central role in developing the concept of using laser interferometry to search for gravitational waves. Kip Thorne helped establish the astrophysical and theoretical case for what such detectors might observe. Ronald Drever contributed important experimental ideas and techniques. The project was developed through the California Institute of Technology and the Massachusetts Institute of Technology, with major support from the United States National Science Foundation. The fact that there are 2 observatories is crucial. A single instrument can be disturbed by countless local events. The ground moves, equipment vibrates, weather changes, vehicles pass nearby. A small earthquake can shake the site. Even distant ocean waves can create subtle motion in the ground. If something unusual appears in only one detector, researchers must consider the possibility that it came from Earth. A true gravitational wave, however, can pass through both observatories. The signal should appear with a delay consistent with the time required for light to travel between the 2 sites. Because the observatories are separated by thousands of kilometers, this provides an important test. The international network extends beyond the United States. The Virgo detector operates near Pisa in Italy. The Kamioka gravitational wave detector operates in Japan. Together, these instruments give scientists more independent measurements of the same passing waves. Additional detectors also improve the ability to estimate where in the sky a signal came from. The 2 United States observatories share the same basic design. Each is shaped like a giant letter L. 2 long arms extend away from a central building at right angles to one another. Each arm is approximately 4 kilometers long. At the heart of the instrument is a device called an interferometer. The basic concept goes back to the physicist Albert Michelson. A laser beam is directed towards a beam splitter. The beam splitter divides the light into 2 paths. One part travels down one arm, the other travels down the perpendicular arm. At the ends of the arms are extremely carefully controlled mirrors. The light reflects and eventually returns towards the center, where the 2 beams are recombined. Normally, the optical system is adjusted so that the returning light interferes in a very precise way. If the relative lengths of the 2 arms change, even slightly, The returning light waves no longer arrive in quite the same relationship. That alters the interference pattern. A passing gravitational wave produces exactly the kind of relative change the instrument is designed to detect. As the wave passes, one direction may be stretched while the perpendicular direction is compressed. A moment later, that pattern reverses. The result is a tiny change in the relative optical path lengths of the two arms. The mirrors are designed to behave as nearly free test masses. They hang from sophisticated suspension systems that isolate them from ordinary movement in the ground. The laser light does not simply travel down each arm once and return. Inside the arms are Fabry-Perot optical cavities. These allow the light to reflect back and forth many times between mirrors. The effective optical path becomes much longer than the physical 4-kilometer arm. That greatly increases sensitivity to tiny changes in distance. The observatories also use power recycling to increase the amount of useful laser light circulating through the interferometer. Signal recycling is used to shape and improve the detector response to gravitational waves. The long beam tubes are maintained under an extremely high vacuum. Without that vacuum, molecules in the air would interfere with the laser and introduce unwanted noise. The mirrors themselves are exceptionally smooth and carefully coated. Their positions are controlled with extraordinary precision. The suspension systems reduce vibrations. Active isolation systems respond to motion in the ground. Every part of the instrument exists because the signal being measured is so small that almost any ordinary disturbance is enormous by comparison. The observatory also behaves differently from a conventional telescope. A normal optical telescope points towards a limited region of the sky and collects light arriving from that direction. A gravitational wave interferometer is broadly sensitive to waves arriving from many different parts of the sky at once. Its response depends on the direction and polarization of the incoming wave, but it is not simply pointed at one object. In that sense, the detector is listening to a large portion of the universe continuously. It is also important to understand what the instrument is actually measuring. A gravitational wave does not simply stretch both arms by exactly the same amount. If everything changed identically, there would be no relative difference for the interferometer to detect. Instead, the passing wave changes the geometry differently along perpendicular directions. One arm can become slightly longer relative to the other. Then the pattern reverses. The detector measures this difference, and the difference is astonishingly small. For a distant black hole merger, the strain reaching Earth may be around 1 part in 10 to the power of 21. Across an arm 4 kilometers long, that corresponds to a change in length vastly smaller than the diameter of a proton, so the task seems almost unreasonable. Build 2 arms kilometers long, suspend mirrors so carefully that they behave almost as if they are floating freely. Send laser light back and forth through an enormous vacuum system. Suppress vibrations from the planet beneath the detector. Then look for a change in distance smaller than the scale of an atomic nucleus. And somehow, it works. A gravitational wave born in the collision of 2 black holes more than 1 billion years ago can pass through Earth and alter the relative distance between 2 mirrors by an almost unimaginable amount. That tiny shift is enough to reveal that space-time itself has moved. The challenge in detecting gravitational waves becomes clearest when we look at the size of the effect itself. A strong astrophysical signal reaching Earth might produce a strain of around 1 part in 10 to the power of 21. That number is so small that it is difficult to picture intuitively. Across an interferometer arm roughly 4 kilometers long, a strain of that size changes the relative distance by far less than the width of a proton. The mirrors do not somehow carry microscopic rulers marked finely enough to display this movement. Instead, the measurement is made using light. Laser light travelling through the interferometer behaves like an exquisitely precise reference. As the light moves along the 2 perpendicular arms, its electromagnetic wave goes through repeated cycles. When the beams return and recombine, the relative phase of those waves determines how strongly they reinforce or cancel one another. If a gravitational wave changes the relative optical path lengths of the arms, even by an extraordinarily small amount, the returning light is shifted slightly in phase. The interference pattern changes. A photodetector at the output records that change. So the experiment is not really trying to place a conventional measuring scale beside 2 mirrors and watch one of them move by a fraction of a proton. It is watching how the accumulated phase of laser light changes as the geometry through which that light travels is disturbed. This also helps explain the difference between displacement and strain. Displacement is an actual change in distance. Strain is the fractional change compared with the original distance. If the same gravitational wave passes through two detectors of different sizes, the strain can be the same in both, while the larger detector experiences a larger absolute change in length. That is one reason the interferometer arms are several kilometers long. A longer baseline turns the same tiny fractional distortion of space-time into a larger measurable displacement. Even then, the signal remains astonishingly small. And unfortunately, Earth is not especially cooperative when someone is trying to measure motion on this scale. The planet is constantly vibrating. At low frequencies, ground motion is one of the largest problems. Earthquakes are an obvious source, but they do not need to occur nearby. Seismic waves from distant earthquakes can travel enormous distances through the planet and disturb sensitive instruments. Ocean waves also matter, as waves repeatedly push against coastlines. They create persistent seismic vibrations that can travel through the ground. Wind can move buildings and surrounding structures. Passing vehicles create vibrations. Machinery operates. People walk nearby. The Earth, in short, has never agreed to remain still for the convenience of gravitational wave astronomy. Sophisticated suspension and isolation systems are therefore used to prevent as much ground motion as possible from reaching the mirrors. But there is an even subtler low-frequency problem. Moving masses near the detector produce their own changing gravitational fields. Air density can change. Ground can shift. Vehicles and other masses can move. These changes exert tiny gravitational forces directly on the mirrors. This effect is known as Newtonian noise. Unlike ordinary vibration, it cannot simply be blocked with better mechanical isolation, because gravity itself passes through the isolation system. At somewhat higher frequencies, another limitation appears. The mirrors and their suspensions possess thermal energy. Atoms and molecules are never perfectly still at ordinary operating temperatures. Tiny thermal motions in the mirror coatings, substrates, and suspension fibers can contribute fluctuations to the measurement. This is known as thermal noise. The materials used in the mirrors and suspensions are therefore selected and engineered with extraordinary care. Then there is the light itself. Laser light arrives at the photodetector in individual quanta called photons. The exact number of photons arriving during a short interval fluctuates. At higher frequencies, these fluctuations create what is known as quantum shot noise. Even if every classical disturbance could somehow be removed, the quantum nature of light would still impose a measurement limit. Increasing the laser power can help reduce shot noise because more photons provide more information. But this introduces another difficulty. Photons carry momentum. When laser light reflects from a mirror, it exerts a minute force. Fluctuations in the number of photons therefore create fluctuations in that force. The result is radiation pressure noise. This becomes particularly important at lower frequencies. So increasing the laser power improves one quantum limitation while potentially making another worse. It is an unusually delicate balancing act. Researchers have developed techniques that make the quantum behavior of light itself part of the solution. One of these is squeezed light. Quantum mechanics places limits on how precisely certain complementary properties of light can be known at the same time. Squeezing rearranges that uncertainty. Instead of allowing the quantum fluctuations to be distributed equally between different properties of the light, physicists reduce the uncertainty in the quantity most important for a particular measurement, while allowing greater uncertainty elsewhere. Used carefully, squeezed light can improve the sensitivity of a gravitational wave detector without simply increasing laser power. The observatories also surround themselves with environmental sensors. Seismometers monitor movement in the ground. Microphones listen for acoustic disturbances. Magnetometers record changes in surrounding magnetic fields. Weather instruments track wind, atmospheric pressure, temperature, and other local conditions. Additional sensors monitor equipment throughout the site. If an unusual feature appears in the gravitational wave data, researchers can compare it with these environmental records. Perhaps there was an earthquake. Perhaps lightning produced an electromagnetic disturbance. Perhaps a vehicle passed nearby. Perhaps a piece of equipment vibrated unexpectedly. Occasionally even local wildlife has managed to become part of the observatory story. But an animal wandering near a detector does not neatly reproduce the complete spiral, merger, and ringdown waveform of two black holes. The purpose of this monitoring is to identify disturbances and understand the behavior of the instrument well enough that genuine astrophysical signals can be distinguished from local noise. Another essential step is calibration. The detector initially produces optical and electronic signals. Those signals must be translated into a physically meaningful measurement of gravitational wave strain. Calibration establishes the relationship between the detector response and the actual change in the relative lengths of the interferometer arms. Researchers deliberately apply precisely controlled forces to the mirrors and study how the instrument responds. This allows the recorded data to be converted into an accurate strain measurement, along with a carefully estimated uncertainty. And then there is one of the most powerful safeguards of all. There is more than one detector. A disturbance caused by local machinery in Louisiana should not produce a matching signal in Washington, with precisely the timing expected for something travelling across Earth at the speed of light. A gravitational wave can, if similar waveform patterns appear in widely separated observatories, with the correct delay between them, the likelihood of a local disturbance explaining both becomes dramatically smaller. With additional observatories in Europe and Japan, the network becomes even more powerful, so by the time scientists speak of measuring a black hole merger, an enormous amount has already happened. Laser phase has recorded a tiny geometrical change. Mechanical and environmental disturbances have been controlled and monitored. Quantum noise has been managed. The detector has been calibrated. Independent observatories have compared what they saw. Yet even after all of that, the gravitational wave does not simply appear as a perfect clean chirp. It remains buried inside a much larger stream of noise. The instrument has measured space-time. The next challenge is finding the collision hidden inside the data. A gravitational wave detector does not produce a neat little message announcing that two black holes have collided. What it produces is data, a continuous, restless stream of measurements containing everything the instrument can sense. Most of that stream is not astrophysical. It includes vibrations from the Earth, thermal motion in the mirrors, quantum fluctuations in the laser light, electronic noise, environmental disturbances, and occasional instrumental glitches. Somewhere inside that complicated background, a genuine gravitational wave may be hiding. Finding it is a little like trying to recognize a familiar melody playing very quietly beneath a layer of static. Except the real analysis does not depend on anyone sitting beside a computer and listening carefully. It relies on mathematics. Before a search even begins, the detector data have to be prepared. This process is often called data conditioning. The raw output is first calibrated so that the electronic response of the instrument can be translated into gravitational wave strain. Researchers then identify periods when the detector was behaving poorly, or when known instrumental problems were present. Certain disturbances can be removed or reduced if their origins are well understood. Other periods may simply be marked as unsuitable for sensitive searches. The data can also be examined in different ways. One useful description shows how strain changes over time. Another shows how the signal is distributed across frequency. Moving between these time and frequency descriptions helps reveal patterns that may be difficult to recognize in only one form. Once the data are prepared, one of the most powerful techniques used to search for binary mergers is matched filtering. The central idea is beautifully simple. General relativity predicts what gravitational waves from merging black holes should look like. So instead of searching blindly for anything unusual, researchers compare the detector data against large numbers of predicted signals. Imagine having thousands upon thousands of possible faint melodies and asking which one best matches the sound buried inside the static. That is roughly the intuition. In practice, matched filtering uses precise mathematical correlations. The predicted signals are called templates. A template represents the waveform expected from a particular kind of binary. Change the masses of the black holes, and the waveform changes. Change their spins, and it changes again. Alter the mass ratio, spin orientations, or other properties, and subtle differences appear in the timing and shape of the signal. Researchers therefore build enormous template banks. One template might represent two black holes of similar mass with little spin. Another might represent an unequal pair, Others cover systems in which one or both black holes rotate rapidly. Together, the bank samples a wide region of the possible compact binary population. The detector data are compared with these templates to see whether any predicted waveform is present more strongly than would normally be expected from noise. Several independent analysis pipelines perform these searches. One is known as the Python Compact Binary Coalescence Pipeline. Another uses tools from the Gravitational Wave Science Analysis Library. Their precise implementations differ, which is scientifically useful. Independent methods can analyze the same data and provide confidence that a candidate is not simply an artifact produced by one particular piece of software. When a template matches the data, researchers calculate a quantity known as the signal-to-noise ratio. This measures, in broad terms, how strongly the data resemble the expected signal compared with the surrounding noise. A larger signal-to-noise ratio generally means the candidate stands out more clearly. But loud does not automatically mean real. Gravitational wave detectors occasionally experience brief disturbances known as glitches. Some glitches can be strong. A few can even resemble portions of astrophysical signals closely enough to produce a large response in a matched filtering search. So researchers need more evidence. One of the most important checks is coincidence between detectors. A genuine gravitational wave arriving at Earth should affect more than one operating observatory. The waveforms seen in each detector will not necessarily be identical, because the instruments have different orientations and respond differently to the direction and polarization of the incoming wave. But the signals should still be compatible. Their timing must also make physical sense. The gravitational wave cannot travel between observatories faster than light, so if related patterns appear in Louisiana and Washington, within the allowed light travel time between the sites, the case becomes much stronger. Researchers then ask another crucial question. How often could noise alone produce something this convincing? To estimate that, they can deliberately shift the data from one detector in time relative to another. The shift is made large enough that a real astrophysical signal could no longer line up between the instruments. Any coincidences produced after that artificial shift must therefore be accidental. Repeating this process many times builds a statistical picture of the background. If signals resembling the candidate occur frequently in these artificial coincidences, the event may not be especially convincing. If nothing comparable appears even after an enormous amount of background data is generated, confidence rises. One way of expressing this is the false alarm rate. The false alarm rate estimates how often noise would be expected to produce a candidate, at least as significant as the one being examined. A very low false alarm rate suggests that an accidental explanation is unlikely. Another useful quantity is astrophysical probability. This asks a slightly different question. Rather than simply estimating how unusual the candidate is compared with noise, it weighs the possibility that the event belongs to a real astrophysical population. The two ideas are related, but they are not identical. Matched filtering is particularly powerful when the expected waveform is already understood. But researchers do not want every search to depend completely on having predicted the signal in advance. That is why gravitational wave astronomy also uses unmodelled burst searches. These searches look for coherent concentrations of excess power appearing across multiple detectors. They do not require the data to match the complete inspiral and merger pattern of a known compact binary template. This makes them useful for detecting unexpected transient signals or checking strong events independently. Once a promising merger has been identified, the analysis becomes more detailed. Scientists then want to know what produced it. This is where Bayesian parameter estimation becomes important. Instead of selecting only one perfect waveform, researchers compare many possible source models with the observed data. The result is not usually a single exact answer. It is a collection of probability distributions. One distribution may describe the likely mass of the heavier black hole, another describes the lighter one. Others represent spin, distance, orientation, sky location, and properties of the final remnant. This is an important feature of gravitational wave astronomy. The measurements come with uncertainty. Scientists do not pretend that a black hole weighed exactly one particular amount or sat at one perfectly known distance, unless the data truly justify that precision. Instead, the analysis describes which values are more likely and which remain possible. All of these techniques came together in extraordinary fashion on the morning of September the 14th, 2015. The detectors in Livingston, Louisiana and Hanford, Washington recorded a short signal. It rose rapidly in frequency. It became stronger. Then it disappeared. The pattern resembled exactly the sort of chirp predicted for two black holes rushing through their final orbits and merging. It was visible in both observatories. Its timing was consistent with something crossing Earth at the speed of light. Independent searches found it. Predicted waveforms matched it. Statistical tests showed that ordinary detector noise was extraordinarily unlikely to explain it. For decades, physicists had prepared to find a gravitational wave hidden somewhere inside the noise. Then, almost as soon as the improved instruments began listening, the universe provided a signal so clear that the hidden chirp was difficult to mistake for anything else. On the morning of September 14th, 2015, two enormous instruments in the United States recorded a disturbance that lasted for only a fraction of a second. It arrived first at the Gravitational Wave Observatory in Livingston, Louisiana. Roughly 7 milliseconds later, a remarkably similar signal appeared at the observatory near Hanford, Washington. 7 milliseconds is almost no time at all by ordinary standards, but for two observatories separated by thousands of kilometers, that delay was immediately interesting. A gravitational wave crossing Earth cannot travel faster than light. The small difference in arrival time was entirely compatible with a disturbance moving across the planet at the speed of light from somewhere far beyond Earth. The signal became known as Gravitational Wave Event 150914, named after the date on which it was detected. Its shape was extraordinary. Over roughly 0.2 of a second, the gravitational wave frequency swept upward from around 35 Hz to roughly 250 Hz. At the same time, its amplitude increased. The waveform rose through the detector band, became strongest near the merger, and then quickly faded. It was the characteristic chirp physicists had spent decades expecting, from two compact objects spiraling together. And when researchers compared the signal with the predictions of Albert Einstein's general theory of relativity, the explanation became remarkably specific. The source was not a pair of neutron stars. It was not an exploding star. It was not an unknown disturbance in one of the instruments. It was consistent with two stellar mass black holes completing their final orbits, merging, and leaving behind one larger black hole. The heavier of the original black holes had a mass of roughly 36 times that of the Sun. The lighter contained roughly 29 solar masses. After the merger, the remnant had a mass of about 62 suns. The difference of roughly 3 solar masses had been carried away predominantly as gravitational wave energy during the final stages of the collision. The event itself had taken place at a distance corresponding to roughly 1.3 billion light-years. That gives the signal a particularly beautiful sense of timing. The black holes had already merged around 1.3 billion years before the disturbance reached the detectors. Their gravitational waves had been travelling through the universe for an immense span of geological time, beginning long before animals or complex multicellular ecosystems became widespread on Earth. For almost all of that journey, there was no instrument here capable of detecting them. Then, just as the waves finally reached our planet, humanity happened to have two of the most sensitive measuring devices ever constructed operating and ready. The timing was even more remarkable because the detectors had not yet formally begun their first observing run in their upgraded configuration. The instruments were operating during an engineering period only a few days before the official observing campaign was scheduled to begin. The universe apparently had not checked the timetable. An automated analysis system recognized something unusual almost immediately. Marco Drago, then working with the collaboration, was among the researchers who received the early alert indicating that a strong candidate had appeared in the data. At first, excitement had to be restrained. The collaboration had good reason to be cautious. Gravitational wave detectors are deliberately tested with artificial signals. During some exercises, researchers can introduce simulated events into the analysis system to make sure that the teams respond correctly. These are sometimes called hardware injections when the mirrors are physically moved in a controlled way to mimic the response expected from a passing gravitational wave. So one of the first questions was obvious. Had somebody deliberately put this signal there? The answer was no. Researchers checked whether a test injection had been performed. They examined the state of the instruments. They looked through environmental sensors. They investigated possible electronic problems. They checked the calibration. They searched for disturbances in the surrounding environment. They considered data corruption and software errors. They examined whether any known instrumental glitch could produce something similar. The signal survived those tests. Even more importantly, it was present in both United States observatories with the appropriate difference in arrival time. Researchers then examined the waveform itself. 2 different types of search recovered the event. Matched filtering analysis found an excellent correspondence between the detector data and waveforms expected from compact binary mergers. A more general transient search, designed to identify coherent bursts of gravitational wave energy without requiring exactly the same detailed model, also detected the event independently. This mattered because the same conclusion was not resting on one piece of software or one particular analysis technique. Then came the comparison with numerical relativity. For years, physicists had used powerful computers to calculate what the final orbits and merger of 2 black holes should produce. Those simulations predicted the distinctive evolution from in-spiral into merger and then ring-down. When the observed signal was compared with numerical relativity waveforms, the agreement was striking. The shape of the chirp was not merely vaguely suggestive of black holes. It followed the pattern expected from general relativity across the most extreme part of the collision. Researchers also needed to know how likely it was that random detector noise could have produced something equally convincing. The answer was extraordinarily unlikely. Background studies indicated that a noise event of comparable significance would be expected less often than roughly once in 200,000 years of comparable observing time. That did not mean the researchers had literally operated the detectors for 200,000 years. Instead, they used statistical techniques, including artificial time shifts between the observatories, to estimate how frequently random noise could accidentally create such a convincing coincidence. The result crossed the exceptionally strict threshold normally demanded before physicists announce a major discovery. Still, the collaboration did not announce it immediately. September became October. October became November. Teams continued checking the data and testing alternative explanations. Hundreds of scientists were involved in confirming what the instruments appeared to have seen. Gabriela Gonzalez, who was serving as spokesperson for the scientific collaboration, became one of the prominent figures involved in presenting the result. David Reitz, executive director of the Gravitational Wave Observatory, also played a leading role in explaining its significance publicly. Finally, on February 11, 2016, nearly 5 months after the wave had passed through Earth, the discovery was announced to the world. That distinction between the 2 dates is important. September 14, 2015, was the day the gravitational wave reached the detectors. February 11, 2016, was the day the scientific result became public. The announcement confirmed something physicists had been pursuing for generations. Gravitational waves had been directly detected. But the discovery did more than confirm the existence of waves in space-time. It also provided the first direct observation of a binary black hole system merging. Before this event, stellar mass black holes were already strongly supported by many forms of astronomical evidence. But nobody had directly observed a pair of black holes spiraling together through their gravitational radiation. The signal revealed both discoveries at once. It confirmed that gravitational waves behave as general relativity predicts. And it showed that binary black holes capable of merging within the lifetime of the universe genuinely exist. The importance of the achievement was recognized 2 years later. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the gravitational wave detector and the observation of gravitational waves. Behind those 3 names stood decades of work by thousands of scientists, engineers, technicians, institutions, and funding bodies. What began as an extremely difficult experimental idea had become a new form of astronomy. And perhaps the most surprising part was how quickly the first extraordinary signal stopped looking quite so solitary. The detectors continued observing. More chirps appeared, then more. Binary black hole mergers went from a phenomenon nobody had directly observed to an entire population that could be studied statistically. The brief signal of September 14th had not revealed one unusual accident in the distant universe. It had opened a window onto a cosmos filled with black holes quietly finding one another, spiraling together and sending the record of their final moments across space-time. A gravitational wave signal may last only a fraction of a second, but hidden inside its shape is a surprising amount of information. The black holes themselves cannot be seen. There is no photograph showing their masses, their spins, or the distance between them. Instead, physicists work backwards from the gravitational wave. Every rise and fall in the waveform reflects something about the motion that created it. One of the most useful quantities appears during the inspiral, while the two black holes are still circling one another. As the orbit shrinks, the gravitational wave frequency rises. The speed of that rise depends very strongly on a particular combination of the two black hole masses known as the Chirp mass. It is called the Chirp mass because it controls much of the characteristic upward sweep in frequency that gives a merger signal its chirping shape. The Chirp mass is often measured more precisely than either individual black hole mass. That is because the signal may contain many orbital cycles during the inspiral, and each cycle provides another opportunity to measure how quickly the frequency is changing. A slightly different Chirp mass would cause the waveform to drift out of step with the observed signal. Over many cycles, even a tiny mismatch becomes noticeable. Knowing the Chirp mass does not immediately reveal the two individual masses, however. Different pairs of black holes can sometimes produce similar values of Chirp mass. To separate them, researchers use more of the waveform. The detailed phase evolution during inspiral helps. The frequency at which the merger occurs helps. The brief ringdown after merger adds information about the final black hole. By combining all of these features, physicists can estimate the mass of each original black hole and the mass of the remnant left behind. Spin adds another layer. A spinning black hole influences the orbit differently, depending on how rapidly it turns and which way its spin is pointing. If the spins are aligned with the orbital motion, they can allow the binary to remain in orbit somewhat deeper into the strong gravitational field before merging. Spins pointing in the opposite direction can alter the timing differently. Misaligned spins can cause precession, making the orbital plane slowly change orientation as the black holes spiral together. That precession can modulate the gravitational wave. The amplitude changes, the phase changes, the way the signal appears in different detectors can change. Then, after the merger, the spin of the final remnant affects the frequencies and damping times of the ringdown. So the gravitational wave can carry spin information from almost every stage of the collision. The ratio between the two black hole masses also matters. When the masses are nearly equal, much of the gravitational radiation is concentrated in the strongest, simplest pattern. If the masses are more unequal, additional patterns can become easier to observe. These are known as higher-order gravitational wave modes. The dominant mode still carries most of the signal in many mergers, but the weaker modes can reveal extra information about the system. They can help constrain the mass ratio, they can improve estimates of orientation, and in some cases they can reduce ambiguities that would remain if only the strongest mode were measured. Distance is another property hidden inside the amplitude. In general, a more distant merger produces a weaker signal at Earth. That sounds straightforward until orientation enters the picture. A binary viewed almost face-on can appear stronger than the same binary viewed more nearly edge-on. This produces what physicists call the distance inclination degeneracy. A relatively distant system viewed in a favourable orientation can resemble a closer system viewed from a less favourable angle. The waveform can provide clues that help separate these possibilities, especially when precession or higher order modes are visible, but the uncertainty can remain substantial. Cosmic expansion complicates the masses as well. As gravitational waves travel through an expanding universe, their wavelengths are stretched, their frequencies are reduced. This cosmological redshift makes the observed waveform resemble one from a more massive binary. The detector therefore measures what is called the redshifted mass. To recover the source mass as it was in the black hole's own local environment, researchers need information about the cosmological redshift. Sometimes that can be inferred statistically from the measured distance and an assumed cosmological model. But for many black hole mergers, there is no bright electromagnetic counterpart identifying one particular host galaxy, so the source redshift is not known perfectly. The detectors also provide information about where the merger occurred in the sky. A gravitational wave reaches different observatories at slightly different times. Those arrival time differences constrain the direction from which the wave came. If two detectors record the event, the timing often restricts the source to a broad arc across the sky, rather than one precise point. That is because many positions can produce nearly the same difference in arrival time between two locations. The orientations of the detectors help narrow the possibilities further. Each interferometer responds differently to the two gravitational wave polarizations depending on the direction of arrival. Comparing the relative signal strengths and phases therefore adds more information. Adding Virgo in Italy and the Kamioka gravitational wave detector in Japan improves this process substantially when the instruments are observing together. With more detectors at different locations and orientations, researchers gain additional arrival times and different responses to the wave's polarizations. The likely sky region can shrink dramatically. This can be especially important when astronomers want telescopes to search for light from an event involving matter, such as a neutron star merger. With binary black holes, the localization may instead help identify possible host environments and improve population studies. None of these measurements are usually presented as perfectly exact values. Gravitational wave astronomy deals naturally in probabilities. Researchers use Bayesian parameter estimation to compare the data with many possible versions of the source. The result is a posterior probability distribution. Instead of saying that one black hole definitely had one exact mass, the analysis describes which masses are more strongly supported by the data. The same approach applies to spin, distance, inclination, sky position, and remnant properties. Credible intervals then describe ranges containing a chosen share of that posterior probability. This is not scientific hesitation. It is a more accurate description of what the measurement truly tells us. Some events provide tighter constraints than others. A lighter binary may remain inside the detector's sensitive frequency range for many seconds and complete numerous observable cycles. Those repeated cycles give researchers more information about the system. A very massive binary can move through the same frequency band much more quickly. Its signal may be loud near merger, yet contain relatively few inspiral cycles. That can make certain properties harder to disentangle. There are also uncertainties in the models themselves. Waveform systematics arise because no practical model can represent every possible physical situation with infinite precision. Detector calibration carries small uncertainties. Assumptions about eccentricity matter because many standard waveform models treat the orbit as nearly circular. If an unusual system retained measurable eccentricity, using an overly restrictive model could affect the inferred parameters. Researchers therefore compare different waveform families, calibration models, and physical assumptions when precision matters. And then there is the famous sound of the merger. The chirp is real in the sense that it represents the measured gravitational wave frequency changing with time. But the detector is not recording sound travelling through space. Space between the black holes and Earth is far too empty to carry an ordinary acoustic wave across billions of light years. Scientists convert the gravitational wave data into audio by mapping the measured frequencies into a sound signal, sometimes directly when the frequencies already fall within the human hearing range and sometimes by shifting them. What we hear is therefore a sonification of space-time changing. Inside that brief rising tone are estimates of two invisible masses, their spins, their orientation, their distance, the direction in the sky, and the properties of the black hole they produced. One waveform can reveal an extraordinary amount, and once the detections begin to accumulate, those individual stories become something larger. Different masses appear, different spin arrangements emerge. Some binaries are nearly equal, others are strongly unequal. Some remnants reach unexpected sizes. The signal from one collision tells us what happened to one pair of black holes. Hundreds of signals begin to tell us what the hidden population of black holes throughout the universe is actually like. The first gravitational wave detection from merging black holes was extraordinary, partly because nobody yet knew how common such events would turn out to be. Then the detectors kept listening. Only a few months after gravitational wave event 150914, another signal appeared. Gravitational wave event 151226 involved lighter black holes than the first discovery. Because lower mass systems move through the sensitive frequency range of ground-based detectors more slowly, this signal remained observable for more orbital cycles before merger. That mattered scientifically. Each extra cycle carried information about the motion of the binary, allowing researchers to test how closely the waveform followed the predictions of Albert Einstein's general theory of relativity. The event also showed that the first detection was not a peculiar cosmic accident. Binary black holes were beginning to look like a population. As the observatories improved and additional detectors joined the network, the picture became richer. On August 14, 2017, Gravitational Wave Event 170814 was recorded by both United States observatories and by Virgo in Italy. For the first time, 3 gravitational wave detectors observed the same binary black hole merger. That extra detector made an enormous difference. With only 2 observatories, the difference in arrival time often restricts a signal to a broad arc across the sky. A third detector provides another independent timing measurement and a different orientation relative to the incoming gravitational wave. The likely source region can therefore shrink considerably. The 3-detector network also provides more information about the gravitational wave polarizations and helps separate the properties of the source from the way it happens to be oriented relative to Earth. Soon, the detections were becoming interesting not simply because another merger had occurred, but because the black holes themselves were showing unexpected variety. Gravitational Wave Event 190412 provided a particularly useful example. The 2 black holes had clearly different masses, making it the first confidently observed binary black hole merger with a strongly unequal mass ratio. That asymmetry changed the waveform. When 2 black holes have almost identical masses, the gravitational radiation is dominated very strongly by its simplest pattern. With unequal masses, weaker higher order modes can become more visible. These additional gravitational wave patterns provide extra information about the system, including its mass ratio and orientation. The waveform was therefore not merely another chirp. It revealed structure that had been much harder to see in earlier, more symmetrical mergers. Then came systems that challenged expectations about how massive stellar black holes could become. Gravitational Wave Event 190521 involved black holes of roughly 85 and 66 times the mass of the Sun. They merged to form a remnant of approximately 142 solar masses. That final object was especially important because it fell into the category known as an intermediate mass black hole. Intermediate mass black holes occupy the broad territory between stellar mass black holes and the supermassive black holes found in the centres of large galaxies. For years, astronomers had strong evidence for black holes at the smaller and larger ends of that range, while the intermediate population remained much more difficult to establish. Gravitational Wave Event 190521 provided clear gravitational wave evidence that black holes in this middle range can form through mergers. The original components were intriguing as well. Stellar evolution predicts a phenomenon known as pair instability. Inside extremely massive stellar cores, sufficiently energetic photons can begin producing electron and positron pairs. That process removes pressure that would otherwise help support the star. Depending on the mass of the core, pair instability can trigger violent pulsations or even destroy the star completely. As a result, theory predicts a range of black hole masses that should be difficult to produce through the straightforward collapse of an ordinary single star. This region is often called the pair instability mass gap. The roughly 85 solar mass component of Gravitational Wave Event 190521 therefore attracted particular attention. Perhaps it formed through an unusual stellar pathway. Perhaps it had already been created in an earlier black hole merger. The observation did not provide one unquestionable origin story, but it widened the possibilities. Even more extreme systems have since appeared. Gravitational Wave Event 231123 became the most massive binary black hole merger announced by the Gravitational Wave Collaboration. Its component black holes were estimated to contain approximately 100 and 140 times the mass of the Sun. The collision produced a remnant exceeding 225 solar masses. The masses alone were remarkable. The inferred spins made the system even more interesting. Both black holes appear to be rotating rapidly, creating a configuration that is difficult to explain through the simplest models of 2 ordinary massive stars evolving together and collapsing. One possibility is hierarchical formation. A black hole produced by an earlier merger can remain inside a dense environment, such as a massive star cluster, and later encounter another black hole. If it becomes part of a new binary, the next collision effectively produces a second-generation merger. Such a history can naturally create unusually massive and rapidly spinning black holes. Dense stellar environments and other dynamical formation channels therefore become especially interesting when systems like gravitational wave, event 231123, appear. Other detections are valuable for a different reason. Some are not record breakers in mass, they are simply exceptionally clear. Gravitational wave event 250114 produced a particularly strong signal that has allowed researchers to examine the final black hole with unusual precision. Its ringdown provides an opportunity to test whether the remnant behaves as the rotating Kerr black hole predicted by general relativity. Researchers can compare characteristic oscillation frequencies, study how rapidly those vibrations fade, and test whether different parts of the waveform describe one consistent final object. The event has also provided a powerful setting for testing Stephen Hawking's black hole area theorem. Classical general relativity predicts that the total horizon area should not decrease during a merger. The estimated horizons before the collision can therefore be compared with the horizon of the final remnant. These kinds of tests were once mainly theoretical ideas. Increasingly clear gravitational wave signals are turning them into observational physics, and the scale of the field has changed just as dramatically as the precision of individual detections. The fifth gravitational wave transient catalogue, released in May 2026, brought the confirmed collection accumulated since the first detection to 390 compact binary signals. The catalogue added 161 significant signals from the second portion of the fourth observing run. Those newly added events were all consistent with mergers involving two black holes. There is an important distinction here. Public alert systems can contain larger numbers of candidate events. Some are reported rapidly so astronomers can decide whether immediate follow-up observations might be useful. Not every candidate ultimately meets the statistical and data quality requirements for inclusion in a confirmed catalogue. This is why different online lists may display different totals. A public candidate and a confirmed catalogue detection are not necessarily the same thing. That distinction also reflects how much gravitational wave astronomy has matured. The field has moved far beyond asking whether black hole mergers exist. Researchers can now examine distributions, they can compare masses, they can study spins, they can search for evidence of hierarchical mergers, unusual formation environments, and gaps created by stellar evolution. And the ordinary events matter just as much as the spectacular ones. A record-breaking black hole may attract attention because it challenges expectations, but dozens of quieter, more typical mergers reveal the shape of the underlying population. One detection proved that the universe could produce merging binary black holes. Hundreds of detections are beginning to reveal how the universe produces them. With hundreds of black hole mergers now available to study, gravitational wave astronomy is beginning to answer questions that a single spectacular detection never could. The important change is statistical. One merger tells us that two black holes collided. Hundreds begin to tell us how often collisions happen, what kinds of black holes usually take part, and how these systems may have formed across the history of the universe. Researchers can estimate the cosmic merger rate by considering not only how many events are detected, but also how sensitive the observatories were while searching for them. A nearby massive merger is much easier to detect than a weak distant one, so the observed sample is not a perfect census of every collision occurring in the cosmos. Once those selection effects are taken into account, the population becomes a new laboratory for astrophysics. Mass is one of its most revealing properties. If black holes formed with every possible mass equally often, the observed distribution would be relatively featureless. Instead, researchers see structure. Some mass ranges appear more populated than others. There are possible concentrations, changes in slope, relatively sparse regions, and unusually massive outliers that are difficult to explain through the simplest models of stellar collapse. These patterns can be compared with models of how massive stars live and die. One particularly important property is stellar metallicity. In astronomy, metallicity refers broadly to the abundance of elements heavier than hydrogen and helium. A massive star with relatively high metallicity tends to lose more material through stellar winds during its lifetime. A similar star born with lower metallicity can retain more of its mass before its core finally collapses. That means low metallicity environments can provide a route towards heavier stellar black holes. Because the chemical composition of galaxies has changed over cosmic history, the black holes merging today may carry information about stars that formed under conditions very different from those in the modern Milky Way. Mass alone, however, cannot reveal every formation pathway. The ratio between the two component masses provides another clue. So do the black hole's spins. Imagine two massive stars born together and evolving as a binary. Their long shared history can influence the orientations of their rotations and their orbit. Under some isolated binary evolution scenarios, the spins of the eventual black holes may therefore tend to have some alignment with the orbital angular momentum. Now consider black holes assembled later through gravitational encounters in a dense star cluster. They may originally have formed in completely unrelated stellar systems. When random encounters eventually bring them into the same binary, their spin directions have no particular reason to line up neatly. Strongly tilted or apparently random spins can therefore suggest dynamical assembly. But nature rarely provides such convenient labels. Stellar evolution can tilt spins. Natal kicks can alter orbital planes. Dynamical systems can occasionally produce apparently orderly arrangements, and gravitational wave measurements of spin orientation are not equally precise for every event. So these properties are clues rather than guaranteed fingerprints. The real power comes from combining many observations. A population containing particular mass ratios, spin magnitudes, spin tilts, eccentricities, and merger rates can be compared with competing models of isolated stellar evolution, globular clusters, nuclear star clusters, and other dense environments. Some systems may even have more complicated family histories. A black hole created in one merger can remain inside a dense cluster. If the gravitational recoil is not strong enough to eject it, it may later meet another black hole. If a new binary forms and merges, one member of that system is already the product of an earlier collision. This is a hierarchical merger. Repeated generations could produce black holes that are heavier than expected from direct stellar collapse, and that carry the characteristic spins inherited from previous mergers. Some unusually massive systems observed through gravitational waves are therefore being investigated as possible hierarchical merger candidates. These same signals can also contribute to cosmology. A binary black hole merger can act as what is known as a standard siren. The gravitational waveform contains information about the intrinsic strength of the source. By comparing that with the strength measured at Earth, researchers can estimate what is called the luminosity distance. The idea resembles the use of standard candles in conventional astronomy, except the distance information comes from gravitational waves rather than brightness from electromagnetic radiation. If a redshift can also be associated with the source, the relationship between redshift and distance can help measure the expansion of the universe. Binary black holes are challenging because they usually provide no obvious flash of light identifying a single host galaxy. But statistical methods can compare a gravitational wave localization region with populations of possible galaxies. With enough events, standard sirens may provide an increasingly independent way to study cosmic expansion. Black hole mergers also offer something even more fundamental. They allow Albert Einstein's general theory of relativity to be tested in a regime where gravity is extraordinarily strong and rapidly changing. The Inspiral tests whether the orbital phase develops as general relativity predicts. The merger probes strongly nonlinear gravity. The Ringdown tests whether the Remnant behaves like a rotating Kerr black hole. Researchers can also ask whether gravitational waves travel across cosmological distances in the expected way. Unexpected dispersion would mean different gravitational wave frequencies travelled at different effective speeds. Alternative theories of gravity can sometimes predict additional gravitational wave polarizations beyond those expected in general relativity. Physicists can search for inconsistencies between the remnant predicted from the Inspiral and the remnant measured from the Ringdown. They can also search carefully for unusual features after merger, including proposed gravitational wave echoes. So far, there is no established evidence requiring such a departure from general relativity. That absence is itself scientifically valuable. Each new merger pushes the theory through another extreme test. Stephen Hawking's black hole area theorem provides one example. The theorem predicts that within classical general relativity, the total event horizon area should not decrease during a merger. With a sufficiently clear signal, researchers can estimate the masses and spins of the two original black holes, infer their horizon areas, and compare them with the area of the final remnant. The no-hair expectation offers another test. Once a black hole is settled, its external gravitational behavior should be described by a remarkably small set of properties, principally mass and spin for an astrophysical black hole with negligible electrical charge. Measuring multiple Ringdown frequencies offers a way of asking whether they all belong to the same Kerr black hole. Future observatories should make these tests far more precise. Cosmic Explorer is a proposed next-generation gravitational wave observatory in the United States designed to achieve dramatically greater sensitivity than the current generation of detectors. The Einstein telescope is a proposed European underground gravitational wave observatory intended to explore a wider frequency range and detect compact binary mergers across much greater cosmic distances. Instead of detecting only the louder fraction of the population, instruments of this generation could observe black hole mergers much deeper into the history of the universe. They could follow more signals for longer periods, recover weaker features in the waveform, and measure black hole properties with much greater precision. A different part of the gravitational wave spectrum will be explored from space. The Laser Interferometer Space Antenna is a European Space Agency-led mission, with contributions from the National Aeronautics and Space Administration. Rather than using kilometre-scale arms on Earth, it will use spacecraft separated by millions of kilometres and measure tiny changes in their relative distances with laser light. Its great size allows it to respond to much lower gravitational wave frequencies than ground-based observatories. This opens access to systems involving far more massive black holes, including binaries containing the massive black holes found in galactic centres. It may also observe some smaller binary systems long before their final mergers. In certain cases, a binary could first be detected in the low-frequency band of a space observatory, and later enter the higher frequency range accessible from Earth. That possibility is known as multiband gravitational wave astronomy. Instead of discovering the system only during its final moments, astronomers could know in advance that a merger is approaching, and then observe different stages of the same gravitational story with different instruments. Meanwhile, the existing observatories continue to be upgraded between observing campaigns. Greater laser power, improved mirrors, better quantum techniques, refined suspensions, and other changes can extend their reach. The precise schedules and configurations evolve as those upgrades are installed and commissioned, because instruments attempting to measure distortions smaller than a proton tend not to appreciate being hurried. What began in September 2015 as one brief chirp has therefore become something much larger. Before gravitational wave astronomy, black holes were studied mainly through what happened around them. Astronomers watched stars orbit invisible masses. They observed gas heating as it fell inward. They studied jets, accretion disks, gravitational lensing, and the motions of surrounding objects. Now there is another possibility. When two black holes orbit and collide, their changing gravitational field produces a direct record of the space-time geometry around them. The waves tell us how massive the black holes were. They reveal aspects of their spins. They preserve hints about where the systems formed. They test how gravity behaves in its most extreme dynamical form. And across a growing population, they are turning objects famous for hiding almost everything behind their horizons into some of the most revealing laboratories in the universe. When two black holes collide, the event is not a simple impact between solid objects. Their event horizons become enclosed within a single common horizon. The newly formed remnant is initially distorted and dynamic, then gradually settles into a rotating black hole described by the Kerr solution. During that transformation, part of the original system's mass energy escapes outward in the form of gravitational waves. The complete journey can begin millions or even billions of years earlier. Two black holes first have to become gravitationally bound. They may descend from a pair of massive stars that evolve together, or they may meet later through gravitational encounters in a dense environment such as a globular cluster. Once the binary exists, gravitational waves slowly remove energy and angular momentum from the orbit. The black holes move closer, their orbital speed increases, the gravitational waves become stronger and rise in frequency. For most of the binary's life, this inspiral may proceed almost imperceptibly. Near the end, however, everything accelerates. The final orbits take place in intensely curved space-time, with the black holes moving at a significant fraction of the speed of light. Then comes the plunge. A common horizon forms. The gravitational wave emission reaches its greatest strength. The system stops behaving like two separate black holes and becomes one violently distorted remnant. That remnant then enters Ringdown. Its space-time oscillates through characteristic quasi-normal modes, losing the remaining distortions through gravitational radiation, until a much calmer rotating Kerr black hole remains. The merger can also give the remnant a gravitational recoil if the radiation is emitted unevenly, leaving the new black hole travelling through space after the event. None of this requires two hard surfaces to strike one another. Black holes do not have crusts or shells. The observable collision is fundamentally an evolution of space-time geometry, and that changing geometry creates the signal astronomers eventually detect. The rising gravitational wave chirp contains a record of the motion. Its frequency tells us how rapidly the binary is orbiting. The way that frequency changes reveals the chirp mass. The amplitude carries information about distance and orientation. The phase evolution contains details about the component masses and spins. Precession and higher order modes can reveal further structure. The merger and ringdown help determine the properties of the black hole left behind. From a signal lasting perhaps only a fraction of a second, researchers can reconstruct an astonishing amount about objects they never see directly. Doing that requires equally remarkable instruments. The two United States gravitational wave observatories at Hanford in Washington and Livingston in Louisiana each use perpendicular arms approximately 4 kilometers long. Virgo in Italy and the Kamioka gravitational wave detector in Japan add further measurements to the international network. These instruments use laser interferometry to measure relative changes in distance far smaller than the width of a proton. The signal is then extracted from noise through several connected methods. Matched filtering compares detector data with predicted gravitational waveforms. Coincidence between separate observatories helps distinguish an astrophysical event from a local disturbance. Background estimation reveals how often noise might accidentally produce something similar. Numerical relativity predicts the waveforms produced during the strongest part of the collision. Bayesian inference then provides probability distributions for the masses, spins, distance, orientation, and other properties of the source. All of those techniques came together on September 14th, 2015. A gravitational wave passed through Earth after travelling for roughly 1.3 billion years. It had been created by two black holes completing their final orbits, merging and settling into one remnant. That brief signal became the first direct detection of gravitational waves and the first direct observation of a binary black hole merger. At the time, it was extraordinary, because there had never been anything like it. Now, it belongs to a catalogue containing hundreds of confirmed compact binary signals, and that growing population has revealed that black hole mergers are far more diverse than the first event could show. Some systems contain black holes with very unequal masses. Others contain rapidly spinning components. Some mergers create intermediate mass black holes. Several observed systems sit in regions of the mass distribution that challenge simple models of stellar collapse. A few may even involve hierarchical mergers, where one of the black holes was itself created in an earlier collision. Each detection therefore becomes more than another entry in a catalogue. It provides another test of Albert Einstein's general theory of relativity under some of the strongest gravitational conditions available anywhere in nature. The signals can be used to examine the Kerr description of rotating black holes. They can test Stephen Hawking's black hole area theorem. They can search for inconsistencies between inspiral, merger, and ringdown. And across many detections, they begin to reveal where black holes come from and how their populations have evolved throughout cosmic history. Perhaps the strangest part of all is the contrast between the event and the measurement. At the source, several times the mass of the Sun can be transformed into gravitational wave energy in an extraordinarily short interval. The power can become almost incomprehensibly large. Space-time itself is being reshaped around two objects moving at relativistic speeds. Then the waves spread outward. They cross galaxies. They pass through intergalactic space. They travel for hundreds of millions or billions of years, and when they finally reach Earth, the disturbance is so small that only some of the most sensitive instruments ever constructed can notice that anything happened at all. A colossal collision becomes a movement far smaller than a proton. And inside that movement is the story of two invisible black holes. Astronomy once depended almost entirely on light. Now it can also detect the changing geometry of space-time itself. Black holes are famous for allowing almost nothing to escape from within their horizons. But when two of them collide, the universe still finds a way to tell us what happened.